Greetings.
Hey, good morning.
I've got something awesome to show you today. Is there any days I haven't said that? I think I say that every day. But I'm not wrong if you think about it. All right. So I'm sharing a screen that has the drawing program that maybe I've shown you a time or two. This is the drawing program that I use to draw house plans on, called AutoCAD. And we're going to need it today because I'm going to show you the foundations of something amazing. So we've been studying in this chapter different ways of representing a function. And so we have a polar choice and what was the other one? Parametric, polar and parametric options for representing equations. And so again, the big picture is we didn't learn anything new. We just learned a new way of representing something we already understood. But we saw that parametric allows you to get time involved, so you can talk about speed of something happening, and polar gave us graphs that were really cool, non-function graphs, and then we applied calculus to those things. And now we're going to look at a class of functions in particular through this lens collectively called conic sections. And they're called conic sections because they're sections of cones. I would encourage you to take a look online at kind of some visuals for that. But I won't do it in the interest of time, but even though I'm suddenly thinking I should. Yeah, maybe I should. Let's just do that right now. It's not going to hurt us, right? How long would it take to Google search conic sections? Not very long. So they're called conic sections because if you take a slice through a cone at different angles, you actually get these shapes. And notice if you slice a cone straight horizontally, it would intersect the cone in a circle. Yet if you slice it at an angle, it actually creates an ellipse. And if you slice it parallel to this angle right here, if you slice it parallel to the angle of the cone, you actually get a parabola. And then if you slice it at a different angle, you get a hyperbola. And that's only just, I don't know, geometrically beautiful, except for these shapes have some incredible qualities about them. And again, I hope your Math 112 teacher, I hate to say this, but did a good job and actually showed you some of this, because that's a part of what's in a Math 111. It's part of what's in a Math 111 class. But these particular shapes actually have some incredibly practical uses in our culture. Here's another shot of them. Horizontal slice circle, angled slice ellipse, slice parallel to one of the faces gives you a parabola, a slice at some other non-parallel angle gives you a hyperbola. And so we're going to look at the equations for these. And again, it's no joke in our culture or in mathematics in general. And I hope these kinds of things aren't lost on you, that you could make a slice like that, but the fact that there's actually an equation that would model that, I mean, those are geometry, right? Like a physical shape, and yet there's a mathematical equation that models those. That was effectively the brilliant observation of Rene Descartes, for whom we have, or for the creator of whom or which was the Cartesian coordinate system, the XY coordinate axis that we just changed. But the fact that he realized there's a connection between algebra and geometry, those were two separate fields that sort of thought they had nothing in common back when math was it's still being invented, but back when a lot of the basics that we study now were being invented. And in a sense, he was responsible for realizing that they're actually connected. I mean, the universe is a little more connected than that. So there's an algebra equation that matches those shapes. And of course, you're familiar with probably the ellipse, the parabola, and the circle from Math 111, maybe not so much the hyperbola. But perhaps you don't know maybe some of the properties that these shapes have. So let's play with this a little bit. So I actually want to make I want to make these for you because I want you to have a really good sense of what these shapes are. So let's do this because I just want to give you some time to kind of process this. So I'm going to draw a line right here and T. This thing is called the directrix. Cool word, directrix. Let's scale that bad boy up about 4 times bigger. So that thing is called the directrix, which is sort of just kind of a weird name. And then we're going to have let's draw a circle out here. So let's go out a certain distance. Go out a distance of 7. And I'm going to put kind of a small circle right here. So that was a distance of 7 out. And that thing is called the focus. So, what in the world, what are these words? What do these have to do with anything? Well, let's go build a parabola. Now, you know a parabola, like you've played with them in algebra. You're actually more familiar with it as an algebra student than you are as a geometry student. So the equation of a parabola is, the basic one is y equals x squared, and then you can mess with it from there. But notice I'm drawing it as a piece of geometry. So actually, just as a point of reference, do any of you have any knowledge about what parabolas are good for besides just being cool curves? Some of you should have. Volume down, or do you have none?
Well, I know they have some certain properties, echo properties, they're used for satellite dishes and other.
Yeah, that's right. They have a property of focusing any signal. So let's take a look at this. So here's what a parabola is if you want to make your own. Now you can't, like if I draw a curve and I say, what is that? Many of you would say, oh, that's a parabola, but it's not going to work. Like it's not a parabola. You know what I mean? But to be a parabola, it's actually got to be constructed either by a graphing calculator or some machinery that can produce a perfect parabola, or by what I'm about to show you. And so it turns out that now if I take this focus point and this line, and I find a bunch of points that are the same distance away from the focus as they are from the directrix. A bunch of points that are the same distance away. What do I mean by that? Well, as an example, let's say 6. I'm going to make a point that is 6 away from the focus and 6 away from this line. So I'm going to use a command called offset. I'm going to offset a distance of 6. So that distance right there is 6. So every point in this line is 6 away from that line, right? Now I need to find the point that is also 6 away from this circle. So in order to do that, I'm going to draw a circle centered right there of radius 6. So would you agree if let's see, I'm going to make if you want to ask me anything about AutoCAD, you're welcome to, but I'm going to fill this point in so that it looks solid. So let's just move that into place. So would you agree that that point is 6 away from the focus and it's also 6 away from the line? Just to make sure you have a sense of what I mean, I'm going to go in here and dimension this. I'm going to take this away, but just so that you kind of make sure you understand what I just did. Hey, look, that's 6 away. Hey, look, that's 6 away. Can you see that there's like only one? Well, there's actually one on the other side on the bottom too. I'll put that in later. But so that a parabola, it turns out, is a whole bunch of points. By definition, the geometric definition of a parabola is it's a bunch of points that are the same distance away from a line as they are from a point. So as you no doubt observed, that was so much fun. Let's keep doing it. So what if I said a distance of, I don't know, 10. So now I go 10 away. That's a lot further. Now I draw a circle of radius 10. And now I have another point that I can add. So there's a point that's 10 away. What about 8? Let's do 8 since I skipped it. Circle radius 8. And what about, I don't know, 4? What about a distance of 4? Remember, the distance between the focus and the directrix, that distance was 7. I just kind of made 7 up. So that means 4 will work. So if I say, let's draw a circle of radius 4, that's where they hit. So can you see the parabola beginning to form here? By the way, wouldn't there be one point right here? Where would that point be? Well, as I said, given that the distance I chose to put the focus away from the directrix was 7, there'd be one right in the middle, right at 3.5. Does that make sense? So just to save time, I'm just going to draw a line there. I'm just going to copy this and put it in the middle of that line. AutoCAD has a snap that kind of knows you want the middle. So, and let's do one larger. So what did I do? I did, was it 12? Is that what I did to get that one? Or was it 10? I think it was 10. Let's do one like 16, offset 16. Now we're way out there. And so then I say I need a circle of radius 16. And notice my line's not long enough, so I'll just drag it and make it a little longer. So you can see the parabola forming, right? And now I'm going to do something fun and use a command called mirror. And I'm going to grab those points and mirror them over to the other side. And so can you see that this is actually forming a parabola, except for this time the parabola is actually a parabola. Do you understand that? Like I didn't do any equations. I just took measurements. Like you could do this in your backyard with a tape measure. You got to be careful and so forth. And now there's a command in AutoCAD called spline, which allows me to kind of click on these points and sort of tries to connect them with a smooth curve. I think I'll just keep going. Whoa. We got to use a different mouse for this. So you likely, if you heard the definition for a parabola, you know, when you're in some math class before this, they probably didn't draw it for you. And so that right there is a collection. The technical definition of a parabola is a collection of points that are all the same distance from one line as they are from one point. And the line's called the directrix because it's an important, you know, it's a line that kind of should have a name, and then so is the focus. And the reason that point's called the focus is exactly because of what Ben just said. Now let's watch this thing work. You probably know this, but let's pretend here comes a, you know, like a ball comes in and it hits this wall right here and bounces. And notice the size of that angle that I just randomly drew. That angle right there is 40 degrees. And so does it make sense that if it hits that it's going to bounce off at exactly the same angle? I'm not going to go into this, but it's a little more complicated than that in physics if energy is lost and so forth. But does it make sense it's going to bounce off at the same exact angle. So physicists say the angle of incidence equals the angle of reflection. It'll bounce off at the same angle. So, okay, well, that's great. Well, then what if a signal, or let's say a television signal, is coming in over here, it's coming into this satellite dish, and then all of a sudden, bam, it hits it right there, right? So take a look at that angle. Now notice if I go over here to dimension and I say angular, it's not going to do it because this right here isn't a straight line. But now, you know, from calculus, isn't that pretty much a straight line right there? And so it's not that there isn't an angle right there. There is, but I won't bother to figure out what it is, but it's going to bounce off. Well, guess where it's going to bounce? If that angle is exactly the same, would you agree it looks like about there? I'm just guessing right now. Does that look about right? Guess where it's going to bounce? Boom. That's why it's called the focus. Does that actually look like those two angles are the same? No. That's kind of cool. So let's see, what size is that angle? That's a fairly smallish angle. But let's send a signal in, I don't know, over here. So here comes another signal, you know, bam, it hits the satellite dish. Well, that's a much bigger angle. Would you agree that's like more than 45 at least, just at a glance? Well, if I bounced off, would you agree it looks like about there approximately? Well, look at that. Boom, goes right to the focus. And so it turns out in a satellite dish, every single signal, and it could be a sun ray. There is a thing called a solar oven that you can take as a backpacker that is shaped like a satellite dish, and it basically has a reflective surface on the back. And you could actually aim this thing at the sun and put your squirrel or whatever it is you're eating out there. You could put it here and then focus the sun on it and basically heat it up. If you had a really accurate satellite dish, you wouldn't want to put your finger there because it would just flat burn a hole in it. It is crazy if you try to concentrate the sun. You probably all at least played with a magnifying glass that concentrates the sun on just a tiny little, disc about this size. If you made that satellite dish a foot wide, I mean, it would burn a hole in your finger. Like you would not want it to feel like a laser beam. But this is a rather remarkable property. And so, it's not just like a section of a cone. Hey, look at that. I sliced it and made this neat curve. Isn't that fun? Humans, if you will, have discovered, and notice, and I like to say discovered, like we didn't make that. Did we make a shape that did this? No, we discovered it. That's just kind of beautiful. And yet it has this purpose. And so we've made all kinds of cool uses of this particular shape. So there's two uses that we make of it. One is collection, and that's what a satellite dish is doing. It's collecting not a sun ray, but a television signal. And it's taking the weak signal that often comes from California. All our satellite dishes are facing south because they're collecting a signal that's coming from California. And then it collects it. And there's always going to be a little collector here, like if it was sound, like on the side of a football stadium, there's a dude on the side that's holding a satellite dish aimed at the field, because listening to sports without sound is really not exciting. So when people all crash into each other and make a bunch of noises, like football. So that person's actually aiming their clear satellite dish at the field, and there's a microphone here to collect the sound. If it was a satellite dish, there's some sort of a receiver there. I don't even know what a television signal is, and so it's not a microphone, it's collecting that signal. So it has the purpose of collecting things. It's not just, it's all kinds of things you could collect, but it also has the opposite effect. The headlights in a car are the reverse of this. You put this weak little bulb right here, a weak little light bulb right there, and then all the light that gets sent out in every direction bounces off the parabolic shaped mirror. My cheap flashlight in the garage has one of these, and then it hits the side and then bounces off. And so it takes all that light and focuses it somewhere. If you just had the light bulb outside, it would just dissipate in every direction and it wouldn't light your path for you. But in this way, you're taking all of the light that would be going in every which direction, and you're saying, no, I want it all to be, aiming out in this parallel beam. And so the headlights in your car are designed with a parabolic mirror at the back of them, and so are flashlights and so forth. So this is an amazing device. So it focuses signals. So that's kind of cool. So let's make this point then. Let's see, let's get rid of some of these things. So let me add one thing here and say this. I'm going to call this length right here for no good reason. I'm going to call it n. So that's length n. And copy that over to there. And I'm going to call this length m. And for a parabola, m equals n. They're the same exact length. That's how we built it. Does that make sense? What questions do you have for me? Or observations or thoughts? I want to just kind of blow by this. What's your thinking there?
Are there any, like, what makes parabolas different than if m is always n, or is that just the parabola we made?
Say that one more time. What makes them? Oh, what makes them all different? Yeah. I chose. I made two choices. One of, let's see, did I make two choices? No, I only made one choice. I said, hey, let's put the focus 7 away from the directrix. Does that make sense? That's the only choice I made, and that produced the parabola. You could probably watch a video someplace on this. Let's see, I'm trying to think if there's any easy way I could do this. Maybe we'll get to that. But if I had chosen that distance to be bigger, it would have made the parabola either wider, like a really long, wide parabola, or maybe it would have made it super skinny. So it'd be nice to kind of make a second one where that distance wasn't 7. And then you could see the different shape. But it turns out that's really all that's going on. Now, in the case of putting it on a piece of graph paper, we have to say, where do you want to put it? Do you want to put what's called the vertex, the bottom? You probably remember that term, that the vertex, that bottom point right there. Do you want to put that at the 0, 0 on the graph, and so it doesn't have to slide around as much? Or do you want to put it somewhere else? But as far as the shape actually is concerned, notice the directrix, the distance between the directrix and the focus determined the whole shape. I only made one choice, and then I made no more choices. The parabola just resulted from that. That's interesting.
And then in terms of like collecting sound or light, like when you want to collect data from outside going in, is bigger always better?
I don't know if I know the answer to that. I'm sort of reasoning out loud. I think that's a wonderful question. My guess is yes. In other words, it's kind of like your ear, like, oh, I can't hear that. But you can sort of see further stars if you have a parabolic refracting telescope. This is the way telescopes work. So the bigger the telescope you have, then the further you're going to be able to see, because you're basically taking a weaker signal. And now that your satellite dish is huge, then you're able to collect something, really massive. Have you seen this? This is really cool. I got to show you this all of a sudden. Oh, we need to look at this. We need to look at this on Google Earth. That'd be even better. Let's look at it on Google Earth. Have you heard of Arecibo? Have you seen James Bond? Let's see, which one was that? Oh man, one of the James Bonds. This satellite dish is in the James Bond flick. I can't remember which one it was.
It's outside though. You can see it on Google Pro.
Yeah, you can see it on Google Earth. So let's go watch it. So Arecibo. This is like the biggest satellite dish in the world. It's in Puerto Rico. Search. I'm really bad at geography. Okay, so we're in Puerto Rico. Let's see, I hope Arecibo, I may have to type I don't know if this is taking us to the town of Arecibo, or actually if Arecibo is the name of yeah, it's not taking us to the right spot. Arecibo Observatory. What am I looking for? Arecibo Observatory. Let's try that. Oh, a little out of town. Okay. So there you are. So there's the satellite dish. Do you see what else is in the picture? What's up here? So there's some cars. There's a car. So now you have some sense of scale. That's rather big. So
And that thing in the middle is the receiver.
yeah, that's exactly right. So you see the shadow of it over there. I'm not sure exactly how well you guys can see this, but that's the receiver, and there's the shadow of it sitting in there. So it's literally so big you couldn't support it. So they just sort of dug it into the hillside. So it's kind of like plowed the hillside out in the shape of a parabola. Now it's a little more complicated than this if you decide to look into it. There are other shapes that can kind of focus things depending on where you put this. And so it's not quite as simple as just build a parabola, put the receiver at the focus. That you can do spherical ones, and this particular one is a spherical. So there's a little more to it than this, but
So that leads me to my last question is, wouldn't you want to put that receiver in a more like convenient place? Like, couldn't you form a parabola to put it to where it's not in the way?
yeah, good question. It turns out that if the signal, like the way I just showed it, is like the signals are coming straight in, so you point it straight at it. But it turns out if the signals are coming in over here, it'll still bounce off and hit a focus, but then it'll move the focus to the side. You may notice the satellite dishes on houses don't have the receiver right at the bottom at the focus. So they're kind of off to the side. And so a signal that came in over here kind of sideways, because you can appreciate you can't just take the earth and turn it whatever direction you want, right? If you're going to have a satellite dish that's that big and it's just built into the ground, it just points where it points. Like you can't point it anywhere. So if this signal comes in and hits right here, let's see, I can't get it to want to land there, and it bounces off at the same angle again, it will still focus at a point. It just is at a different location. And so there's a lot of neat stuff to this. And so in the case of that observatory, you may have noticed that, and I just showed you a picture that somebody took of it, that collector, if you will, is hanging from 3 or 4 towers around there, and they can basically just move it anywhere they want. And by doing that, they're basically focusing it at some different place in the universe to either send or receive a signal. So you got to watch that James Bond flick. It's awesome. The bad guy falls off this and falls all the way to the ground and dies, and then this whole thing falls on top of him, and so he dies in glorious fashion after being a bad guy. But it actually gives you a look because they're running around inside here, and they're a bunch of the movies based on it. So, but anyway, I mean, the cool part of this is just, look what people figured out. I mean, we're studying something called a conic section, and yet people have found a way to harness this to do amazing things, to send and receive signals from space. Amazing. Now let's take this same exact design and do something different with it. And this is what's weird about this. I'm going to take this same exact setup, except this time, instead of letting m equal n, let's let m equal 0.75 n, or 3/4 of n. And I've already spoiled it, but you might say, what would that do? What if I don't make those lengths equal? You might think, oh, it's still going to be a parabola, but it doesn't. Can you picture the parabola actually just keeps going out and out and out and out forever? But watch what happens here. This is really crazy. So let's see, I need m to be 3/4 of whatever I pick n to be. And so I chose that 3/4 just kind of randomly. I just chose it to be something different. Before it was 1m equals 1n, and now I said, oh, let's make it 3/4 the size. So as an example, if I said, let's offset this a distance of 8. So my n value is 8. Well, if I take 3/4 of 8, I get 6. And so that means I need m to be 6. So my circle now will have a radius of 6. And I plot that point. Boom. Just get rid of those. So again, just to make sure you're kind of like, okay, what just happened now? So I said this distance right here is 6, but this distance over here is 8. So sure enough, m is 3/4 of n. And so I'm just going to repeat this a little bit. Just going to play with that for a little bit now. So I don't know, offset 12. That's an easy one. 3/4 of 12 is 9. So if I make a circle of radius 9, now I have another point that I can plot. Copy. Stick that dude over there. This is the reason, by the way, that I chose 7 earlier, because if I make this distance 4, then this distance here would be 3. And I wanted to be able to locate that point right there, kind of the vertex of it nicely. So that's why I chose 7 earlier, so that 3 plus 4 was 7. So do you agree that point's located correctly? So let's see, let's choose. So that distance was 4. Well, let's do a distance of 6. Notice this is the first one I chose that isn't so nice. Let's see, 3/4 of 6. Well, it doesn't come out so nice, but I can just say 3/4 times 6, that'd be 18/4. So I can say circle with a radius of 18/4. I don't even need to reduce that. And so there's another point. So would you agree this is, well, it's just, I mean, had I not stupidly spoiled the beans, you'd say, well, that's a parabola too. Like it's just going to go out and out and out. But let's keep going. Offset a distance of 16. So 3/4 of 16 is 12. So if I draw a circle of radius 12. So again, you would still say, yep, look at that. It's just a skinnier parabola, right? It's just looking skinnier, but let's go out to 20 now. What about offset a distance of 20? 3/4 of 20 is 15, I think. So if I say I need a circle of radius 15, something weird happens. For the first time now, uh-oh, that's not a parabola. I thought this was a parabola, but it isn't a parabola, because that point just dropped below the previous point. I don't know, offset a distance of 21. No, I just did 20. Let's do something bigger. Offset a distance of 22. A circle. I got to take 22 times 3/4. That'd be 66/4. I don't even have to figure out what it is. So I'm just choosing sort of hundreds of points. Offset a distance of 24. That one's going to be easy because 3/4 of 24 is 18. A circle of radius 18. Again, I'm purposely kind of drawing this for you a little bit because I just want you to have a deeper interaction with this. If I just kind of put it up there, I mean, I could have done this all before class and said, look, there's an ellipse, there's a parabola, but it's like, I want you to watch it get built because you should be able to build this. Let's see, what about, I don't know, I got to 24. What about 28? Offset a distance of 28. That's an easy one because 3/4 of 28 is 21. Circle of radius 21. Ooh, whoa. Notice I got really lucky there. Like I actually just found the end. I just found the end of the parabola. Notice it just barely touched it. In other words, if I go further, offset a distance of 32, 3/4 of 32 is 24. If I draw a circle of radius 24, notice it doesn't hit it now. Like there's no point. It didn't make it. So it's a set of points. Geometrically, an ellipse is a set of points that are not the same distance from the focus as they are from the directrix, but a defined proportion of that distance. So I just found the other end. And so let's, again, to save time, I'm just going to grab all of those and put them on the other side. Does it make sense? The other side, I could have been putting 2 points down every single time. And now I don't know how good this is going to do, but I'm going to try the spline command and see if I try to connect all these, if it'll do it. The thing I'm concerned about is it doesn't know, this command does not know I'm sort of trying to make a parabola or trying to make an ellipse. All it does is try to create a smooth curve to connect whatever points I happen to choose. But does it make sense if I stop right there? The ends of it are going to be pointed. Does that make sense to you? So I don't know, it doesn't take too long. Let's just go connect them all. I think, notice how that right end looks pretty good down there, but I think when I get to this other end, I think it's going to be pointed. I don't think it's going to work. See how it's all screwed up on that side? So it looks good down here. I guess we could say that. And I suppose I could do something somewhat creative here and there's a command in here called trim, and I could click this and trim that off. So now I just have the right half of it, and then I could mirror that to the other side. But I technically though, I guess I'd like you to understand that the shape that I just drew is a pretty good approximation for an ellipse, but that's still not perfect because that's just some interesting mathematical command that connects all those points together. Anybody know? I mean, isn't that weird though, that so this is saying if I connect these, starting to act like I'm complicating it. Isn't that weird that it connects this shape? Does anybody know what properties this shape has? What the reason that you study it? Why is this shape really cool? I think I just overwhelmed it. This is used for a really cool medical device. Now I'm not going to be able to show you because it's acting like it's freaking out. And I didn't.
Is it an ultrasound?
Yeah, it's kind of related to ultrasound, but it has the property. Think of that as like let's pretend that was like a pool table where you had like an elliptical shaped pool table, and you had a ball at the focus over there. I don't know if you can picture this, but there'd be another focus on the other side that'd be in the same symmetrical location. But if you took that pool ball at the focus on the right-hand side and you just hit it any place on the wall you want, just hit it anywhere, it's going to bounce off the wall and it's going to go to the other focus. Now, the property and think about the way the ellipse worked, or the way the parabola worked. How did it work? Well, when it bounced off the wall, where did it go? It went out parallel in that direction. So it focused them all parallel. What does this one do? Well, when it bounces off of here, it actually hits this and then it refocuses at the other focus. And so what's done medically is you take a device that emits a radioactive signal that will like destroy something cancerous, or a gallstone, or whatever, something in your body. I don't know much about medical stuff. Something in your body you want destroyed. Maybe it's cancer and you're trying to just hit it. Well, the problem is you can't just like shoot radiation into people because it like kills other organs. Well, this thing is called a lithotripter, and you basically put it against the side of somebody. You have this weak signal, just like the weak light bulb, a weak signal that bounces off of this, and it goes through your body, but as long as it's a weak signal, it doesn't hurt you. But if you can get the other focus to be right on the part of their body that you actually want to destroy, then all those signals will recoalesce right at that spot and concentrate and actually theoretically just kill the thing that's at that focus and like not hurt the rest of the body. I mean, that's a brilliant invention. So I mean, that's a use people have made of it. The other thing that's really cool about parabolas and ellipses is this is how things fly through space. We are orbiting around the sun. We are flying along the path of this ellipse, and the sun is at one of the focuses. And that's also true for other things. I don't know if you've heard of Halley's Comet, but you only see it like every 70 years because most of the time, here's the sun and here's us flying around the sun. Most of the time, Halley's Comet is not over here really close to this focus where we in the sun can see it. It's usually way out in space for most of those years, so far away that we can't see it. And so it's on a really long, skinny ellipse, if you will. It has a low or a high eccentricity, it's called. We'll get to that tomorrow. And so that's why we know as much as we know about space. And when people say, oh, Halley's Comet is going to come on this day at this time, and same with like, oh, there's going to be a solar eclipse. You know, how do people know that stuff? It's because we understand mathematically that that's what's happening in space. Things are flying on an ellipse. They also fly along parabolas. If something is flying through space and it gets within the gravitational pull of anything, say the sun or maybe something smaller like us, it'll bend its path around it and then it'll take off into space again and kind of never come back. So sometimes they'll get caught in orbit around it and just stay there. And other times it'll just bend them and then they go back off in space again. So isn't that weird that it's like these things are mysteriously and beautifully all collected into a cone? It's like slices of a cone. And this is only two of them. And yet they model things in space. They have properties that focus signals in a way that is just really cool. One time I was in a room that had an elliptical ceiling. And I don't know if you've ever had the opportunity to do this, but if you ever do, you've got to go there. But sometimes they're called whispering rooms or something like that. But the ceiling was elliptical. And as it turned out, so imagine this from the side, I'm sitting here and here's the ceiling over the top of me. And there's somebody else over sitting on the other focus. And in this particular case, I was sitting there minding my own business, working on something, just sitting in a chair. It was in the kind of the open area of a really fancy hotel. And all of a sudden I hear this dude, and this dude is like right here in my ear. I mean, it literally sounds like somebody put their mouth 2 inches from my ear, and I turn to look and there's nobody there. And there's clearly somebody talking, and I start looking around like an idiot, you know, what the heck, where's that coming from? How's this happening? I don't understand what's happening. And eventually I see a dude across the way whose mouth is moving in exactly the same way of which I'm hearing in my ear. And I realized, oh my gosh, I mean, I knew about this principle before, so at least I was able to figure it out. But like that person's voice is really weak and I can't hear it across the room because there's other voices and other sounds of people doing things. I can't hear him. But what's happening? Well, every single signal of his voice, which goes out in every direction, hits the ceiling, and then it travels along and it recollects over at the other focus where my ear is. That's why I was hearing him, because it was collecting all the sound that would have ordinarily been lost, right? If you're sitting in a room and talking to a person, the only sound you hear is the sound that goes straight from your mouth to their ear, although the rest of it is lost and wasted. So, I mean, these are really cool things. They're useful, they're neat. Anyway, let's play around now. Man, I'm so disappointed that went into the death spin because I wasn't done playing with it, but at least we got it to there. Wow, that's like frozen, like I can't even stop sharing frozen. That's not good. I'm gonna try to end AutoCAD. There, that worked. I got rid of it. All that cool drawing is lost now. So, share screen, start writing. So I alerted you yesterday to a note sheet that I posted in my open math, the note sheet that you'll have for this next test. And as soon as it stops spinning, I'll be pulling up for you. But it lists kind of a bunch of properties about these shapes and, you know, the ability to kind of work with these and understand where's the focus and where's the directrix. And, you know, if you did build a parabola, so to speak, where would the focus actually be? What's the connection between kind of the algebraic equation for the ellipse or whatever and its counterpart? You know, how does that all work? We're failing the share test right now. And so you might pull that up. If you haven't already done that, at least have access to it electronically so you can stare at it. Because again, this is kind of our final push toward this chapter 12 test, but there's, you know, a lot of stuff to remember. Like you wouldn't not want to have to remember it. So let's see if we can, I don't know, do a little better than that. So we're going to first look at the Cartesian version of these equations. It turns out there's a Cartesian version, which you're already somewhat familiar with. Like I said, y equals x squared. That's a Cartesian equation with y's and x's that tells you the equation of a parabola. And you already have some sense of kind of how that works. But what we're going to look at here first is the Cartesian version of these a little bit today. And then we're going to look at the polar version of them tomorrow, because that's also kind of cool. So what you should be less familiar with, although as I said, I hope your Math 111 teacher actually has already showed you much of what I showed you today. I hope you already kind of knew some of that. If you didn't, that's okay though. We're talking about it now. But take a look at that note sheet with respect to what it says about parabolas, because it's, you know, how do I figure out where the focus is? I mean, if I drew an ellipse or a parabola or something before, you would have just said, hey, look, there's a circle, there's a parabola, but you never thought about a focus for it. But now you realize, at least as a practical component, this thing is produced based on a directrix and a focus, and to know where those are and so forth is kind of an important part of this. Just a second, I'm not sure why my machine is in spin mode here. So it's not wanting me to share a screen. That's not very nice. That's okay. I don't see anything wrong with that. Let's see, what are my options here? Well, I guess to start with, I will share not my iPad, but just the sheet that I was referring to, since at least I can get to it over here. So what I'm talking about is those formulas right there. So part of this you should recognize. In other words, if you have an equation that has just a y and an x squared, or just an x and a y squared, that's going to create a parabola. If they're both squared, both y squared and x squared, then you're going to get either an ellipse or a circle. And by the way, do you understand a circle is just a special case of an ellipse? That's why there's no formula here for a circle. A circle is a special case of an ellipse that kind of has the same radius vertically as it does horizontally, but usually, you know, one radius is a lot longer than the other. And so anyway, that's what I want to play around with. I guess since we're here and I can't share, at least right now, let's just go ahead and bring up Desmos over here. My computer is kind of old. I actually ordered another one. I have a feeling that that's part of the problem that I've had with this machine. Hopefully it will work. So the point is, you're used to seeing, a parabola look like that. And so, but the question of this is like, so that's in a sense, the most generic parabola I could draw. And notice how much less trouble that was than what I just did a second ago in AutoCAD, right? To actually build one. It's really nice to have an equation that tells you how the points are related to each other and not have to physically measure each one of them. But where would the focus of this be? Can you figure that out from the note sheet? Where would the focus of this be?
At like 2, right? Y equals 2.
So let's graph that. Let's see if, so I'm graphing the point 0, 2. So in a sense, that's Bayes' conjecture. You agree with him?
Is the formula 1/4a for a focus?
Yeah, there's more than one way that
Okay.
this is written. I actually don't like the way your book writes it, but I decided not to circumvent it. But notice it's y equals x squared, except for there's this 4p there. Well, there's a 4 and a p, and p is the distance from the vertex to the focus. And in the case of a parabola, that's also the distance from the vertex to the directrix. Remember, the vertex is like the pointed part of the parabola. So those distances were equal. So P is that distance. It's like the M and the N that were equal to each other, so to speak. Well, notice what's in front of ours. Ours says y equals x squared. So that number is a 1. Isn't that 1y squared? I'm sorry, 1y equals x squared. And so that's a 1. Well, in order for this to be a 1, what does P have to be? This is why I find this confusing. P would have to be a 4th. Because isn't 1/4 times 4 1? So P's got to be a 4th. So that distance is actually a 4th. So it isn't 0, 2. It's a 4th. That would be the focus. Now I can't draw on this quite as easily as I could before, but can you see it working? Like if I came down, if this is the signal coming in from right here, and it hit right there and it bounced off to the focus, does it look like those two angles are the same? Does it look like that's working? I think it does. And then in the case of a parabola, the note sheet says this distance right here is a 4th. And since that distance is the same as the distance to the directrix, does it make sense the directrix would be the equation y equals -1/4? Is that right? Is it y? Yeah, so there's the directrix. Like I found the equation of the directrix and I found the actual coordinate of the focus. And so that's just something to be added to this. I mean, if you want to use a parabola for something, you'd have to understand that. You'd have to understand, in a sense, I think of the directrix as like the ground on which you built your satellite dish. So the red is the collection of all the points that are the same distance away from the blue point as they are from the green line. So I think of this as the focus point where I'm going to put my microphone, and down here is the ground on which I'm going to build this satellite dish, and then I just find these points. And so yeah, an equation is really cool. It's really nice. Can you remember this from your earlier math classes? What if I stick something like, I don't know, 0.2 in front of that? What's going to happen to my parabola if I say 0.2? Is that what you thought it would do? That's the A value in front of it. It's like the slope. I just made the slope smaller. The slope used to be 1 and now it's 1/5. Well, now the slope is wider and it's lower. And so it made the graph lower. Does it make sense? The focus is not where it was before. Can you do the math off my sheet? My sheet says y 4 times p times y is x squared. Notice this number is not in the right location. It's got to be over there with the y, right? So I don't really like the way they worded this. If I move this to the other side, isn't that 0.2 1/5? And if I moved it to the other side, wouldn't that be the same, since you can get away with this in this machine? Wouldn't that be the same as putting a 5 over here? Isn't that the same graph? So what does that make p? So it says, so basically 4 times p has to be 5, right? Because we need that to be a 5. So then I got to sort of figure out what P is. 4 times P equals 5. If I divide by 4, I guess it's 1 1/4 then, right? P would be 1 1/4. Well, that's your focus distance. And so now this would be 1 1/4, 5/4. There's where the focus would be. And my directrix would also be down there now. So do you see what it did? It's like a wider parabola is going to have a focus that's further off the bottom of the satellite dish, if you will. That's kind of what that's getting at. See that working? What does it take to make an ellipse? And by the way, notice this said vertex at the origin. And notice that was the case. The vertex of that really was at the origin. So, you know, we don't want to mess around with, you might remember if I replace X with X minus 4, that would slide it right 4. But the cool thing about this section is we're not thinking about this as on some weird location on the graph paper. It's just a shape. Like I want to build it. So let's put it in the easiest place possible. That's the easiest place possible. Same with Y. I could replace Y with Y plus 2, and then it would slide down 2. Well, I don't want it down 2. I just want the shape. So if there's just a shape, then let's just leave it X squared and Y. And then all we have to do is put a number in front of it. And that number just changes the way the shape looks, changes where the focus is and so forth. But how does an ellipse work? Well, notice its basic equation, its generic equation. Again, this should not be brand new to you, but notice it's also centered at the origin, the center of it, not the focus, but the center of it's at the origin. Notice it's just X squared, not X minus 2 squared, just X squared. And there's one number below X and one number below Y. And if you think of those numbers as being squared, then that A value actually tells you, and this is my own language because I think it speaks more clearly, A, the number with the X, is the X radius. So let's go take a look at that. And B is the B radius. And then we'll talk about this formula in just a second, but let's just at least go graph one. So let's see, you're saying that if I took X and squared it, but divided this by some number, and because we wanted that number to be square rootable, since it was squared, then it'd be nice to pick numbers like 4 and 9 and 16 for this instead of like 7 and 12 and 18. So I'm going to pick 4. So what the note sheet said is that's going to give me an X radius of 2. Whereas if I go over to the Y, and this was a plus sign, very important, and I divide this by not 4, but 9, and this is all equal to 1, that will create an ellipse. Notice the number under the X squared is a 4, the square root of which is a 2. And sure enough, the X radius, and do you understand that these aren't radiuses? Like in a circle has a radius, an ellipse doesn't have a radius. But I just said in quotes on my note sheet, the X radius. So notice that really is 2. And then, you know, 3 squared is 9. And notice the Y radius really is 3. And so that's kind of cool that it translates geometry to algebra so neatly. So that's really cool. But again, the question is, where's the focus for this ellipse? Like what, you know, where would it be focusing this? Where is the focus? Well, it'd certainly be along this major axis right here. Notice this particular ellipse happens to be kind of oriented vertically. It's along the major axis. I don't know, I'm just going to take a guess. You think 0, 2? You think maybe it'd be right there? Notice there'd be another one at 0, -2. If I was right about that. So is that the 2 focuses? Can you appreciate if you wanted this to work as a whispering room, or you wanted to make a lithotripter, like you got to know where those are. You can't just kind of be like, oh, that looks good. Where would those actually be? And you don't know anything that would tell you that just yet. Let me change this a little bit because it'll probably be easier for you to see. I wish I could draw on this, but I cannot. I'm gonna make that the 9 and that the 3 for a second. Turn these 2 guys off. Do you agree the major axis is now sideways, which means I could potentially make my same guess here, but then it would have to be 2, 0, wouldn't it? It'd have to be sideways. Now the major axis of this on which the focuses would be. And again, this is why I spent so much time drawing this shape for you. So you'd have more of a conceptual understanding of what produces this shape. That the major axis being horizontal, that kind of determines where these two focuses would actually be. And so that looks reasonable, I would say. So here's something that turns out to be true. I'm trying to say if I've ever made a model of this before. I'm gonna go search. I have a feeling I made a model for this before. Back on May 19th, 2020. Yes. So there's the top half of an ellipse, except for in this case, I made a bunch of things slidable. And let's see, which one am I sliding? I want you to stare at the distance between this focus and the point on the ellipse, and this distance between the other focus and the point on the ellipse, that purple line right there. I want you to pay attention to that distance, because again, what I'm proposing to you, and you can actually see what I told you before in action now. Do you see that this angle over here, do you notice that black, you calculus students, what's the name for that black line? You should know those.
Tangent line.
Tangent line. Notice, if you will, the ball that I hit this way thinks it's hitting that black line. Do you understand that? It doesn't think of itself as hitting an ellipse. It says, oh, I'm hitting that black line. Do you agree that the angle between the black line and the purple line over here looks exactly the same as over there? Do you see what it's doing? It's actually, no matter where I've moved this thing to, it's actually refocusing that signal to the other focus. That's why if you sort of hit a ball from one focus on the elliptical pool table, so to speak, it's going to bounce off and go in that pocket, no matter where I hit it. So that's an amazing property that, again, we've harnessed. And so that's really cool. It's really powerful. Well, let's go right there. That's a really interesting location. What do you know? Does anybody have a conjecture about the length of those purple lines? Notice over here, small line, big line.
Well, they're obviously related as a triangle with the bottom distance is the hypotenuse.
Correct. They're kind of related as a triangle. It isn't always a right triangle. Notice that angle at the top is not 90. So you're calling this a hypotenuse down here visually, but it's got to be, technically, it's got to be a right triangle for that to be a hypotenuse, but it makes a triangle. So that's exactly true. And notice this length down here never changes. That whatever that distance is between there, that distance isn't changing. You see how much of a mess this all is. That would take too long to write a program. I guess I'll just have to tell you. It turns out that in this particular shape right there, this distance right here plus that distance right there stays the same every single time. And so that's another way to actually draw an ellipse, by the way. And I've built elliptical arches in houses that I've built before, and that's how you make them. You actually nail a nail in a piece of plywood over here, and you nail a nail in a piece of plywood over there, and you tie a piece of string to this one, and then you stretch it tight with your pencil at this point right here, and then you just trace along like this, left and right, and it actually produces a perfect ellipse, which just looks cool. Like, I didn't do that because I wanted it to focus sound in my house or whatever. I just did it in an archway, like in one spot in my house. And so you have to know all the math that I'm showing you today to physically produce that, because I needed this arch to be a certain size. So it turns out that's why this system works, is because what the string is doing is making sure the collective sum of this distance plus this distance is exactly the same. So if that's the case, and I put it right here, notice there's, in this case, a Pythagorean theorem relationship that Vail kind of alluded to. In this particular spot, notice I could actually break this into a right triangle that's sitting over here. Do you agree that, well, actually, what are we calling in the equation that I have written on my note sheet? What are we calling that distance right there? The y radius? What are we calling that distance? That's distance b. That's distance b, and that's the same thing that I have sitting over here. That's distance b. How long is the string here, though? That's kind of an interesting question. How long is the string? And for the fun of it, let me make this a little bit, let's make it what we just did a minute ago. Let's make it 3 and 2. So notice I made this one draggable. So there's the one we were just looking at a second ago. Notice where the focus is. It's not in a very nice location. But I want you to notice something right here. If I move this over to here, you could actually tell me how long the string is. When it's laying right there, right on the edge, I lost it. Where is it? Right there. You should be able to tell me how long that string is now. Doesn't it go from this focus all the way, bam, hits the side of the ellipse, and then it goes back to that focus again? Do you agree with that? So if that's true, then how long is that string for this ellipse? Who can tell us?
Like
Those
3.75.
in the points and times twice the focus length.
What do you get for a number for this ellipse?
Six.
That's right, it's actually 6. It's, and I think Caesar said this too. If you go from this focus all the way to this edge, and notice that's some weird distance because I don't really know where this point is right here. It gets to that edge, but then it turns back that same distance again. Well, if I took that little piece of string right there and put it over here, then isn't that length of the string just the width of the ellipse? It's like the length of the major axis. So in this particular shape, because it was 3 over here and 3 over there, that means that distance is 6. I know how long that string is. It's 6. It's basically 2 times, well, whatever the major axis is. In this case, the major axis is horizontal, so it's the length of the major axis. That's how long your string is. That's kind of cool. So actually, no, in this case, that's the length of 6. Well, what if I move this thing back up to this location up here? Would you agree that this, because they're now split evenly, would you agree this is a length of 3? And we know this is the length of 2. So think Pythagorean theorem. What am I going to do with my 3 and my 2 in order to get this distance right here, which is where I need to know where the focus is? What do I need to do?
Add them and then square root it.
Yeah, well, not add them. Think a little more carefully about that.
Subtract them.
Yeah, notice Pythagorean theorem, you'd be adding these two, this length of 2 plus this length, whatever it is. So if I square this and add those, that would be the purple one, but the purple one is 3. If I took 3 squared minus 2 squared, that'd be 9 minus 4, that'd be 5. Then this distance would be the square root of 5. So on my calculator, if I take the square root of 5, it is, the square root of 5 is 2.236. Notice that's exactly where that point is graphed at. Can you see that it is a little bit short of half of 2.5? It's like 2.125, somewhere in there. I'm sorry, 2.25. It's a little short of 2.25. So that's why my sheet says this statement right here. The square root of a squared minus b squared. 3 minus 2. It's those two values. It's Pythagorean theorem. That's the distance from the center along the major axis to the focus. So you can actually find the focuses by using those A and B values. So that's kind of cool. How's your brain? And one of the things that's not on my note sheet, because it's a little less relevant, would be like, where's the directrix out here? Because remember, this distance right here, whatever that distance is, that was shorter than the distance to the directrix. So that distance is like, what is that, 0.5, 0.75, you know, approximately 0.75 from there. So this distance out here is more than that, like 1 or 1.2 or something like that. We'll talk a little bit more about that tomorrow. Notice you can have really low, kind of flat ellipses. That's Halley's Comet orbit right there. Notice how close the focus is out to the end when you do that. This is why you can't see Halley's Comet very often. Here's the sun at one focus, and then here's Halley's Comet coming in. And so because it's close to the sun here, and then we orbit around the sun, then we see it for a while it's over here. Notice I didn't graph the bottom half. But then it takes off into space, and you know, by the time it gets here, it's like, oh, I can't see it anymore, and I won't see it for the next like 72 years until it comes back around the other side. And so I don't know if you know this, but at least I thought I've heard that Pluto, which is, I guess it's being called into question as maybe not being a planet after all, but Pluto was not discovered accidentally by somebody pointing a telescope. It was because things weren't behaving correctly out there. And so they said, well, the only way that that's the case is if there's something gravitational pulling on it out there. And so based on this math right here, they said, well, it must be right there. It must be, there must be a planet at this focus at this point right here, because that's where planets are. If they have gravitational field, they're at the focus of the orbit that they're causing some smaller object to go around them. And so it's like, well, mathematically it has to be right there. And then they just focus the microscope or the telescope and went, yep, there it is. So Pluto is at least an object, but I guess it's been recently called into question as maybe not being a planet. I don't know why that is, but it's kind of sad for Pluto, don't you think? So what happens if I make them equal? What if I go 4 and 4? That's why I said the circle is a special case. What happened to the focus? How come there's only one focus now?
They're both on the same point.
Nice job. They're both at exactly the same point. Watch what happens if I make B 4.1. So, or even closer, 4.01. This is what we're doing around the sun, by the way. Our orbit is basically circular. It's really close to being a circle. And so this is in a sense, that red shape is kind of unrecognizably different than a circle. Notice it looks like a distance of 4 here, and it looks like a distance of 4 there. But if you get closer, oh, you know, oh, that is 4. If I get closer over here, oh, you know, that's a hair bigger. Oh, that's a hair bigger than 4. I didn't see that. And so circle's just a special case where the two focuses are exactly at the same location. That's kind of cool. So what happens? I don't know if I could copy outside of this. Apparently I can. So let me just make up a quick problem. I'm going to make that a 5 and this a 2. Could you tell me the coordinates of the focus? Let's just find this top focus up here. Could you tell me what coordinate to type based on the equation that I showed you a second ago? I'll put the equation back up quickly in case you're not looking at it. Did you notice on my note sheet that if you subtract the two numbers, subtraction is a dangerous operation because if you subtract the wrong way, you get a negative number and we're supposed to take the square root of it. So that's not good. But I put an absolute value in there so you can subtract any way you want. So if I take this 5 and square it and that 2 and square it, so I get 25 and 4, and I subtract those and I get 21, that's your focal distance, the square root of 21. So if I say I'm going to graph the point, what's wrong with what I'm typing here? Square root of 21, 0. What's wrong with this?
You gotta switch the X and the Y there.
Yeah, you got to go along the major axis. And so in this case, the major axis is not horizontal, it's vertical. So I got to say, oh, that was dumb. I went backwards. There we go. There's the focus of this ellipse. Notice it's fairly long and thin. So that focus point is, way up at the top. It's really close to that end up there. So again, I mentioned this, we'll talk about eccentricity tomorrow, but this has an eccentricity or that's closer to 1. If an eccentricity is closer to 0, then the orbit is circular. If it has an eccentricity closer to 1, like a minute ago when I drew an ellipse, our 0.75 was that number, that kind of multiplier. That made the ellipse more like this one, kind of longer and flat. So that's kind of cool. So last thing for today, we're about out of time, but watch this. What if I go in and make that a minus sign? That's it. That is a hyperbola. Notice a hyperbola it's the same exact equation as ellipse, except it's a minus sign. But notice, like, which one did I pick to be minus? Does that make sense? I chose the y value to be the minus. So the x got to be positive, the y had to be negative, right? So what does this say? Which one is that? Let's see, x was positive. It's this one. And so what does that do? It has a horizontal major axis. And then it says it has asymptotes at y equals plus or minus b over a x. What the heck does that mean? B over a. Horizontal major axis, b over ax, huh? So what you're saying is, if I say y equals b, which is 5, over a, which is 2x, and that could be either plus or minus. Oh, okay. Yeah. All right. Now I see what's going on, you should say. What are those curves? Now, again, would you agree with the untrained eye? You would have said that red line's a parabola, right? You'd have said that's a parabola. But there's more than one curve. Frankly, from this view, if I didn't have these here, that shape right there could be part of an ellipse. It could be part of a parabola. It could be part of a circle. You have no way of knowing. There's lots of other curves too. Those are just a few of them. But this particular one lays down against an asymptote. Parabolas do not do that. In other words, it's not crossing into, those red curves are not crossing into this kind of triangular area up here. It's never going to make it. It's laying, that's kind of how you define it, is it's laying against this shape. It's laying against that sort of cross of lines right there. And again, I doubt you know the answer to this, but it's like, what good is this shape? Is there why is this something we study? Why is this one of the curves we study? Again, crazy that this shape is also what you get if you slice a cone in the right way. You have to have one cone on top of another to get this slice, but what purpose does this serve? I don't know as this serves a lot of purposes. I have read that this is the shape of the cooling towers on radioactive reactors. I don't know if you've ever seen, there's one in Washington. If you drive down the freeway, you'll see it sitting beside the road up there. But I've been told that these do an excellent job of deflecting wind. If you're a future engineer, it turns out that wind is a really big force. Like, it wants to blow buildings over, and it's really powerful. And so if you have a building and wind is hitting it, does it make sense when wind hits this, it you know, the wind kind of wants to slide along it, whereas if it's a flat surface and it hits it, it's going to have to move. But if it's kind of roundish, then the wind would hit it and kind of slide along it, maybe deflect so much of the kind of the pushing force. So I don't know if that's true. I've read it in enough places that I think it is, but I don't understand the math behind it, like why that would be the case. So that's the only kind of application that I've read about this. Let's see, just for the fun of it, what happens if I make this number, you know, bigger? What does that do? Oh, it makes it skinnier. If I make it closer to the same, notice how they're both 2. So that just kind of affects, and you can, maybe you can see the lines, because of course down here, couldn't I, you know, change this to a B and this to an A and graph that? So see how it stays asymptotic to that curve. That's kind of fun, right? And if I go, what's going to happen? You should be able to tell me this. What's going to happen if I make the X the negative and the Y the positive? Oh, it's vertical. Now, again, this is a little harder to tell what the major axis is, and I haven't drawn this for you yet, but it turns out these have focuses too, and they have directrixes as well. Like it can be drawn in the same exact way that I drew for you at the start of class, the parabola and the ellipse. So we need to look at a few more things about this. But this one has a major axis that runs this direction. So that's considered a vertical major axis. And so that's why the note sheet says, if the X is negative and the Y is positive, then it has a vertical major axis. And notice the asymptote equation is, well, the reverse. It's A over B. I actually didn't notice that. It looked like it was working to me. Didn't that look like it was working? I didn't switch it. I think it looked like it was working because I had, let's see. I'm a little flummoxed by this. Oh, I know why. Notice where the A is switched, just to kind of keep the positive one positive. Notice here the A is under the X, whereas down here the A is under the Y. Which actually, I'm looking at that thinking, I must have had a reason for that, but I'm looking at it thinking that seems dumb. Why not leave them alone? And then this equation would be able to be left alone. I have to think about that. Maybe I copied what was in the book, and maybe there's some deeper reason that has to do with the vertex and so forth, but I don't know, we'll look at that. Anyway, I got to shut up for today, but kind of neat shapes, right? So we looked at circles, ellipses, parabolas, and hyperbolas, and all of them have the same exact equation, as it turns out. They're the same type of equation. Going out the door, I will perhaps maybe blow your mind with something here. AX squared plus BX plus CY squared plus DY plus, I can't say E because E is 2.718, so I'll just say K for constant equals 0. What shape is that? Notice it's like a, well, a nothing. It's non-existent. What shape is that? Oh, it's a parabola. I'm sorry, it's an ellipse, right? But then if I drag it over here, all of a sudden it's, well, it's a hyperbola. If I drag it right there, no, it's a parabola. What is it? Well, that's all of them. Like there's one equation that's all in this form. And notice this is not a great form because you can't tell where the ellipse is and so forth. This equation allows that parabola, ellipse, hyperbola, circle to be any place on the graph you want if you just choose the right A, B, C, D, K. But depending on what the relationship is, notice if I choose a negative number for A, that would mean X is negative, but the Y squared is positive. That's why it produced a hyperbola, because one was positive, one was negative. If they're both positive, and you know, sometimes you get no graph. I'll leave you to think about that, but let's see. Notice that looks pretty circle-like. That's kind of interesting. So it looks pretty circle-like. Maybe it's still an ellipse, but it's, you know, pretty close to. If I change this, it kind of gets bigger and smaller, as you can imagine a constant would do. Why does that look circle-like? Does anybody know? Take a look at the numbers that I chose. It has to do with this A and this C, because those are the numbers in front of the important terms. Notice how they're almost the same, 4.2 and 4. That's not a
Yeah,
circle.
if you unfoiled it, it would be almost a circle.
That's
If it was 4 and 4, it would be, right?
That's right. If I back that 4 off, and so now it's 4 and 4, that's actually a circle now. So if A and C are identical, it makes a circle. If one is positive and one is negative, then now it's a hyperbola. And so that's just, I mean, again, isn't that amazing? Like the order of the universe. One equation is all of these, and one shape, a cone, allows you to slice and make every one of these shapes geometrically. Again, I find that there's a great video by three blue, one brown, 3 brown, 1 blue.
Yeah.
That guy does
Blue
a
one
really
brown, yeah.
good video on this. Like he was saying, as an explanation for, you know, like, why do you like math? You know, if you like math, people think you're weird. So it's like, why do you like it? Well, it's because of amazing, beautiful things like this. Now, can you get lost in the details of, I can't find the directrix, and I got a C in that class because I couldn't use the formula to find a directrix, and I couldn't do calculus to figure out its area. It's like, yeah, you can get lost in the details, but to think that there's one equation that creates all these shapes, and that every one of these shapes has a neat property that we use in our culture to do cool things, and that they can all be found by just slices out of a cone. I mean, that's pretty cool. You gotta, maybe you don't want to wade in that far, but man, that's a really beautiful thing. So there's an introduction, at least a kind of a quick introduction to these shapes and some of the basic formulas. And then tomorrow we're going to actually look at the polar version of these equations. And it turns out there's one polar equation that does all of them too. And so that's amazing. So we'll play with that a little bit tomorrow. You actually know enough to do a lot of your math, your online assignment right now. So you could wade into that and play around with it. All right, let's get out of here. I'm way over time. I guess I have no notes to post because everything I did was recorded today, but I'll post the video.